Hello everybody, this is Mr. Coker again, and we'll be doing Module 9. Module 9 is Organic Chemistry. So this is carbon-based chemistry, if you remember from Chem 1, and it's based on carbon chains, carbon rings, and the main thing to think about as you study Module 9 is trying to learn as much as you can about the different functional groups. These are the ways we can alter that carbon chain, adding other elements, maybe adding double bonds and triple bonds, and how that we can get different families of organic chemistry. There are millions of organic chemicals, so how do we organize them? How do we classify them? How do we make some sense out of so many different molecules? We group them into families based on their functional groups, and so it's important to learn as much as you can about these functional groups and to learn what they are. This is going to be a very important module in interpreting your molecule on your poster. The prescription drug that you are using on your drug project poster is an organic molecule, and you're going to need to be able to identify its functional groups. And functional groups very often will lend polarity to a typically nonpolar organic molecule. So, without further ado, let's learn all we can about organic chemistry. So an organic compound is made from carbon atoms. So it'll have one or more carbon atoms, usually has hydrogen atoms as well, and so the simplest organic compounds are just carbon and hydrogen. It may also contain oxygen, such as an alcohol or an aldehyde or an ether. Sulfur is possibly going to be attached to the carbon chain, so can nitrogen be in the carbon chain, or halogens like chlorine or bromine. If we compare organic compounds to inorganic compounds like water, we find that typically the organic compounds are going to have covalent bonds, low melting points, because they are small organic molecules. They don't typically have small covalent molecules. They don't typically have very strong attractive forces between them, so they have low melting points, low boiling points. They're also flammable. The carbon can turn into carbon dioxide by reacting with oxygen. The hydrogen can turn into water by reacting with oxygen. That's always going to be an exothermic reaction, so we call that a combustion reaction. And because of their nonpolar nature, when there's just carbon and hydrogen, you're always going to be nonpolar. Because they are nonpolar, like dissolves like, they're going to be soluble in nonpolar solvents, like hexane. But they're not going to be soluble in water. It is possible to get some organic compounds to dissolve in water. Your drug project molecule probably has a certain solubility in water, but that is accomplished by adding functional groups to the carbon chain. If you just have carbons and hydrogens, you're not going to be soluble in water. So to put organic versus inorganic side by side here and do a comparison, the bonding in organic molecules is mainly going to be covalent bonds, because carbon, hydrogen, oxygen, sulfur, nitrogen, and the halogens are all nonmetals. So nonmetals bond with each other covalently. The bonding in inorganic compounds, well, we think about water. Water is covalently bonded. Salt is inorganic. Salt is ionically bonded. So inorganic does not have one particular type of bonding. But organic, you're usually going to be looking at covalent bonding, sharing electrons. Because of the weak intermolecular forces, inorganic compounds, melting points and boiling points are usually low. On the other hand, inorganics are usually high. The flammability of organics is high, but the inorganics are usually low, and so the ability of the organic molecules to combust. So if we look at the bonding in organic molecules is based on sharing electrons. You share the valence electrons. Carbon has 4 valence electrons. Hydrogen has 1. So if you were to put carbon and hydrogen together in this ratio of 2 to 6, C2H6, you would find the carbon would share one of its electrons with one hydrogen and end up sharing a pair that way. And that would be 6 of those would be spread out among the 2 carbons, 3 on each. and that would leave carbon with one electron to share with the other carbon. So in this case we have carbon sharing 4 pairs, getting its octet filled up, its 8 electrons around the center atom filled up, and hydrogen gets a duet, but then hydrogen is in the first row of the periodic table. It's the first energy level. It only needs 2 electrons to fill up its energy level. And as a result, we have what we call single bonds between the carbons and the carbon and the carbon and the hydrogens. In the basic Lewis structure or structural formula approach, we replace the shared electron pairs with lines. And so on the right we see a Lewis structure of C2H6 ethane. The bottom formula, CH3-CH3, is a more condensed version of the structural formula. It does not show the carbon-hydrogen bonds, but since carbon-carbon bonds can be single, double, or triple, this one happens to show that it's a single bond. So this is called, the molecule is called ethane. So if we look at ane as the ending of the ethane, this actually would be in the first family of organic compounds called the simple alkanes, or the alkanes. Alkanes are made up only of carbon and hydrogen, so no other elements besides carbon and hydrogen, just carbon and hydrogens, and the carbons are bonded to the other carbons with only single bonds, no double bonds, no triple bonds. So when you have simple alkanes made up of only carbons and hydrogens with single bonds, then these are always going to have to be nonpolar, because carbon-carbon, carbon-hydrogen bonds are nonpolar, so there's no polarity to these molecules. That means they're insoluble in water. Their density will typically be less than water, so if you pour an alkane like say octane in water, it will float on the water. It's flammable. The carbons and hydrogens can make carbon dioxide and water, combustion, and it's a very exothermic reaction, used for a lot of energy production. If you think of burning gasoline in your car, you're burning alkanes and making carbon dioxide and water coming out the tailpipe. The first 4 alkanes would be methane, which has a formula of CH4, a carbon surrounded by 4 single-bonded hydrogens. The one we saw on the earlier slide, ethane, C2H6, propane, C3H8, and butane, C4H10. These are the first 4 simple alkanes, and they're all gases, although propane and butane can be liquefied pretty easily by putting them under pressure. So cigarette lighters, which have, if you look through the plastic case of a cigarette lighter, it has a liquid inside that's under pressure. That's butane. Butane lighter, C4H10, but under pressure the gas is compressed into a liquid. Propane in a propane tank, like you would use for a grill, or like I have a big silver propane tank in my backyard that I use partly for heating my house and for cooking for the cook stove, C3H8. It's liquefied, but it's under high pressure in the silver tank in my backyard. Alkanes with 5 to 8 carbon atoms, which would be pentane, hexane, heptane, and octane, are going to be liquids at room temperature. These are one of the main components of gasoline. Gasoline is a liquid at room temperature. So ways we can write the alkane formulas. We sort of started this out with C2H6 before and showed you the expanded formula with all the bonds showing, a condensed version of the formula in which we just show how the carbons attach to each other, and we assume that you know the hydrogens are going to be single bonded because hydrogen can only make one bond. And then the very simplest version of an alkane formula would be something like C2H6, which just lets you know how many carbons and hydrogens, but doesn't attempt to show you how they fit together. So that would be called a molecular formula. So an expanded formula, a condensed formula, a molecular formula. More information in the expanded, less in the condensed, and even less in the molecular formula. You can tell an alkane when you look at the name of an organic compound because it will end in ane. It's got a suffix, A-N-E. So when you see the suffix A-N-E, Think only carbons and hydrogens and all single bonds. Methane, CH4 has one carbon. Ethane, CH3CH3 or C2H6 has two carbons. Propane, C3H8. Butane, C4H10. Pentane, C5H12. You may remember the formula that if you double the carbons and add 2, that you'll get the number of hydrogens. And hexane, C6H14. So the structural formula is simply, this is a condensed formula actually here, a condensed structural formula, just showing that you have a carbon with 3 hydrogens on the left and a carbon with 3 hydrogens on the right, and then sandwiched between you're going to have carbons with only 2 hydrogens. So if we take a look at this one here, counting our carbons, we have 5 carbons in a row. We have 3 hydrogens on the left carbon, 3 hydrogens on the right carbon, and 2 hydrogens in the middle. So if we were going to practice writing a condensed formula for this, we would start on the left, we'd say CH3, and then we would have CH2, 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 and then finally end with CH3. The molecular formula would be just the number of carbons, C5, followed by the number of hydrogens, H12. Because it has 5 carbons and the prefix for 5 is pent, we would name it pentane, ane because the carbons are all single bonded and you have only carbons and hydrogens. It's an alkane, pentane. So check our work. Yep, CH3, CH2, 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 CH3, C5H12, pentane. So these are the simple alkanes. Now we're going to branch out into functional groups. Functional groups are going to add different properties to the simple alkanes. And one of the properties that it very often adds is a degree of polarity. And so it is the organic compounds that have functional groups that are sometimes soluble in water and are polar. Functional groups also add chemical reactivity. If you just took hexane, it wouldn't be a very good drug, but if you add some functional groups, then it will interact with the body in certain ways, and you can have a prescription drug that has some action to it. So functional groups also are how we bring organization to the very millions and millions of organic compounds that exist. We try to bring some order to that by grouping the different families by their functional groups. So this is a characteristic feature that's going to behave in a predictable way. You put a particular functional group on a molecule and you're going to be able to predict what that's going to do to the behavior of that molecule. So it's usually an atom or a group of atoms that you are adding to the molecule. A lot of times these groups are going to replace a hydrogen, and so you'll take a hydrogen off and replace it with some group of atoms. And it gives us a way to classify the families of the organic compounds. The first functional group, and this is very closely related to the alkanes, so we actually call them the cycloalkanes. The first thing you can do to alter the structure of a chain of carbons is to wrap it into some kind of circle. So to make it cyclic or cyclic, cycloalkanes. Here we see 5 carbons wrapped into shape of a pentagon, and because you do not have the hydrogens on the ends, there are no end carbons anymore. You don't have 3 hydrogens on the end carbons, you only have 2 on every carbon. So this would be C5H12. Or sorry, not C5H12, C5H10. 5 carbons, 10 hydrogens. So these are cyclic alkanes. They have 2 hydrogen atoms fewer than the open chain would have. C5H12 would have 2 more than C5H10 cyclopentane. And we simply put cyclo in front of the name of the alkane. So this is C5H12 was pentane. Wrap it into a circle, take off 2 hydrogens, cyclopentane. So that's your first functional group, is the cycloalkanes. Then another thing you can do without adding any new elements is to change up the bonds so that you have double or triple bonds. If you have double bonds, it's called an alkene. So notice the change in the suffix from ane to ene. So carbon chains with double bonds are called alkenes. Carbon chains with triple bonds are called alkynes. A-L-K-Y-N-E-S. So with two carbons, that prefix was eth. So the one on the top there on the right is called ethene, and the one on the bottom would be called ethyne. Change the suffix, and you tell someone what the bonding, how the bonding has changed. So this brings up another vocabulary word, saturated versus unsaturated. When all your carbon bonds are single bonds, you are said to be saturated. The hydrocarbon is saturated. In other words, it's saturated with hydrogens. It's got the most hydrogens you can fit on those carbons because you are limiting your carbons to single bonds. So notice on the left, the formula has 8 hydrogens. When you add double or triple bonds, then you are making the hydrocarbon unsaturated, which means with double or triple bonds, you will have fewer hydrogens. So it's not saturated or full of hydrogen. So fewer hydrogens attached to the carbon chain than alkanes. Alkenes have double bonds, alkynes have triple bonds. These are all unsaturated hydrocarbons. So when the bonds are all single, they're called saturated hydrocarbons. When you have double and triple bonds in the chain, they're called unsaturated. Now, to remind you how this connects to medicine, we have various fats, and we'll be talking about fats in the next module, but we have fats that are called saturated fats, and then fats that are called unsaturated, or sometimes even polyunsaturated fats. You might remember that it is the unsaturated fats that are actually healthier for you. The saturated fats tend to clog up the arteries worse than the unsaturated fats. The double bonds tend to change the shape of a fat in such a way that they do not fit side by side as well, and so the intermolecular forces are not as strong. And so unsaturated fats tend to remain liquid, whereas saturated fats can collect and turn solid, which can cause the clogging of the arteries problem. So if you look at some various oils that you might buy at the store to use for cooking or for making things that you want to eat here, coconut oil is very high in saturated fats, so coconut oil would not be considered a very healthy fat, right? Maize oil or corn oil has more unsaturated fat than saturated fat. Probably the best one on the list here looks like maybe soya oil or sunflower oil. High amounts of unsaturated fats compared to the saturated fats. So there are, we do need fats in our diet, but we want to try to improve on it by using unsaturated fats. Now, one thing about these, we call them oils because they are liquid at room temperature. There are some fats, such as the fat in bacon fat or butter, which will be solid at room temperature, and those are always going to be your saturated fats. You may have heard of omega-3 fats. Omega-3 fats are simply when you have the first double bond in the chain of carbons, and these tend to be long, 20 carbon long chains, something like that. The first double bond is at the third carbon, then you have those omega-3 fats that you see on infomercials and touted as very healthy fats. Okay, now we're going to add our first other element besides carbon and hydrogen to make our functional groups. We have the haloalkanes. The haloalkanes are where you take a hydrogen off and replace it with a group 7, or sometimes you call it group 17, element called a halogen. And so these are called haloalkanes. And these are never found naturally in nature. They're always man-made. Haloalkanes do not occur naturally, but can be made and have quite a few properties that lend itself to things like freons for refrigerators, to make refrigerators work, or various solvents that are haloalkanes, but these are altered synthetically to add chlorine to an alkane chain. The alkane, the halo molecule, the halogen molecule or halogen atom added to the haloalkane is going to tend to make it more polar, which will make it more soluble in water. Now let's look at adding oxygen to a molecule that has carbon and hydrogen. If you add oxygen branching off of a carbon chain with a hydrogen attached, so in the top right box there you have an OH, the red is O and the white or gray is H. If you add an OH, that's called an alcohol. So the OH is called the hydroxyl functional group. Very similar to hydroxide, but hydroxide is an ion. Hydroxyl, YL, suffix would be the OH covalently bonded to the alcohol, to the carbon chain to make an alcohol. These tend to be polar. We know alcohols like the alcohol in drinks in alcoholic beverages is polar. But as its size increases and you have more carbon chain and less OH in comparison, the solubility will decrease. And so something like octanol with 8 carbons in its chain and only 1 OH would not be soluble in water. Another way to add oxygen to a carbon chain is to put it in the chain between the carbons, and that's called an ether. Notice these two molecules have the same chemical formula, C2H6O, but one has the OH as a branching off OH as a hydroxyl group, and this one on the bottom has an oxygen between carbons. That's called an ether. So you would draw it as C-O-C would be your functional group there. Adding the oxygen to the carbon chain tends to increase the solubility in water, and so alcohols and ethers are a lot more soluble in water than their counterparts that only have carbon and hydrogen, the alkanes. This is because the oxygen in the ether or the oxygen in the alcohol can hydrogen bond to the water, and like dissolves like, and if you can form strong enough bonds with water, then you can dissolve in water. The alcohols and ethers with 1 to 4 carbons tend to be soluble, but you get too many carbons in the chain, like 5 carbons, and you lose that solubility. So you'll find in your drug project that adding oxygen to your drug molecule tends to increase its solubility. Another way to add oxygen is to double bond an oxygen to the carbon chain. So instead of single bonding it like an alcohol and ether, you could double bond it. If your double bonded O is bonded to the end of the carbon chain, as it is in the top there, it's called an aldehyde. If it's bonded somewhere in the middle of the carbon chain, it's called a ketone. A carbon with a double bonded O is called a carbonyl group. A carbonyl group, C double bonded O, on the N carbon is an aldehyde. A carbonyl group between carbons, sandwiched between carbons, is called a ketone. So these are two more functional groups. So far we have cyclo, where you make a circle with them. Double bonds are alkenes, triple bonds are alkynes. We've done haloalkanes when we add a halogen to it. We have alcohols, add the OH group. We have ethers, put an O between carbon chains. We have aldehydes, a double bonded O on the N carbon, and ketones, a double bonded O in the center. Definitely want to take good notes on these and rehearse them before the test over this or quiz over this on Friday. Okay, our next type of functional group is called carboxylic acids and esters. Now instead of just adding 1 oxygen, we are going to add 2, one of which will be double bonded and the other will be single bonded to the carbon chain. So this can happen in 2 ways. You can have a carbon double bonded O on an N carbon and an OH on an N carbon. So this would be like an aldehyde combined with an alcohol. The carbon double bonded O, remember, is called a carbonyl group. The single bonded OH is called a hydroxyl group. If we put those two names together, we get the functional group name carboxyl group. These are always going to lower the pH of water. They're going to be soluble in water and lower pH, so they're called carboxylic acids. The one on the right here on the top happens to be acetic acid, the one found in vinegar, which is an organic acid. It has a carboxyl group, a COH double bonded to an O. So now we're adding two oxygens, and in a certain pattern this way, it's called a carboxylic acid. And it will lower pH and dissolve in water. If you tweak it a little bit, and instead of having OH, you put another carbon on there, instead of a hydrogen, you have what is called an ester. These are all very nice smelling, fragrant type of molecules. So it's like a carboxylic group sandwiched between carbon atoms. It doesn't just have to have one carbon on the end. It could have more than one carbon coming off of the O. So if you think about it, this is kind of a ketone ether combination, and it's called an ester. So esters are another type of functional group. So just a quick review, we've worked our way from the simple alkanes, which are just single bonded carbons and hydrogens, to the cycloalkanes, where you wrap the carbon chain into a circle of some sort, like a cyclopentane. Double bonded carbons are called alkenes. Triple bonded carbons are called alkynes. Haloalkanes, if you add halogens instead of hydrogens to the outside of the molecule. And then we had the alcohols with the OH group, hydroxyl group, the ethers with the O sandwiched between carbons, the ketones and the aldehydes with the double bonded O's, and now we have the carboxylic acids and the esters. Very important to study these functional groups. You need to learn these functional groups, what their structures are and what their names are. If instead of oxygen we add nitrogen, then just adding nitrogen is going to create a family called the amines. Nitrogen always forms 3 bonds, so if you put the nitrogen on the N carbon, you'll have an NH2 group. If you put the nitrogen between carbons, you will have an NH group, but these are all called amines. Amines are a nitrogen with 3 branches coming off, and one of the things it bonds to is carbon. So it could possibly bond to 1 or to 2. And these are called amines. If you pair an amine group with a carbonyl group, you have an amide. So here we see on the right, on the bottom, an NH2 and double bonded O attached to the same carbon. So this is a little bit like a carboxylic acid, but instead of an OH, you've got an NH2 in its place. And these are called amides. You can also add in sulfurs. Sulfur will act like oxygen, but usually it won't occur in the chain. Usually the sulfur will branch off as an SH group. So if you think about it, it's a little bit like an alcohol, in that it's an OH group coming off, but instead of being a hydroxyl, we call it a thiol. Thiol. So methane thiol, ethane thiol, 2-propane thiol. Thiols typically occur in nature as in foods that have disagreeable odors. So we all know those foods that sort of maybe taste pretty good, but really kind of smell like garlic and onions and cheese. So that's usually what you're smelling, is the thiol molecules with this SH group. Okay, let's get away from organic functional groups and let's switch over to chemical reactions. that organic compounds can undergo. The first most important reaction to remember for organic compounds is that they will burn. They're combustion reaction. So remember Module 5a, we talked about the 5 different types of reactions. Combustion is one of them. If we balance the following combustion reaction, CH4 plus O2 yields CO2 plus water, and energy, of course, created. We would find that we would want to get the hydrogens balanced by putting a 2 in front of the water, and then balance the oxygens by putting a 2 in front of the O2. So don't forget, combustion reactions are part of organic chemistry as well as inorganic chemistry. Heat is usually a product of a combustion reaction, so combustion reactions are, you guessed it, exothermic. Another kind of reaction is to add things to a double bond by breaking the double bond. If you're adding hydrogen to a double bond, then you are hydrogenating the double bond. So on the first reaction, we see that we have a double bond between the middle 2 carbons. If we break that double bond, we can add an H2 molecule. We can saturate the unsaturated hydrocarbon. Saturate it with hydrogen. You may, if you're a label reader, have seen things like hydrogenated corn oil. That just means that they've taken the double bonds and they've added hydrogen to make it more solid. Or you can hydrate. Hydration is the addition of water. And in a chemical reaction with a double bond, adding water means you add H to one of the carbons and OH to the other carbon. And so you make an alcohol out of an alkene and water. So an alkene and water can make an alcohol. An alkene and hydrogen can make an alkane. Another thing you can add to a double bond would be some halogens. If you add chlorine to a double bond, then you have 2 chlorines attached to 2 neighboring carbons, and so you'd have a double haloalkane. Okay. Sometimes double bonded carbons can react with each other and form long chains. These are called polymers, or plastics. The plastics that we have in our lives are man-made polymers made from simple hydrocarbons with unsaturated double bonds, which breaking the double bond allows them to string the carbon chains together and make them very long, sometimes thousands of carbons long. And this makes them solid and flexible and a lot of usefulness to our lives. So they are large, long-chain molecules. In nature, polymers are used by plants and by our body. Things like cellulose and starch and proteins and DNA. These would all be examples of natural polymers. The synthetic polymers like polyethylene, polystyrene, styrofoam, Teflon skillet, nylon socks. These are man-made polymers, but they're going to be strings of simpler units called monomers. And so the monomer is the small molecule which then strings together like beads to make a long chain molecule called a polymer. So these monomers tend to be small alkenes. Alkenes because you need to be able to break a double bond in order to string these together. So here's some examples of polymers that you might run into in your daily life. The water bottles and soda bottles and bottles that we package things in are polyethylene. Polyvinyl chloride makes a vinyl records, the old style of music. The vinyl that's in your garden hose, these are vinyl chloride. Polypropylene is used in textiles, clothes. Teflon, polytetrafluoroethylene, it's a halocarbon actually, and it's used to coat things and make them more slick so that they have non-stick coating on pans. Saran wrap would be an example of polydichloroethylene, and then polystyrene in a fluffed up very low density form is what we call styrofoam. Okay, changing gears again. Let's talk about what we mean by isomers. We did cover this in Chem 1, but just to remind you, isomers are when you take the same set of atoms and put them together differently. So in other words, you would have the same formula, you would just have a different structure. Structural isomers are when you change the structure. So here we see two isomers of the same formula, C4H10. One has all 4 carbons bonded in a chain. The other one has 3 in a chain with a branching off carbon. So these would have different properties because they have different structures, they have different properties, but they have the same formula, C4H10. So same molecular formula, different arrangement of atoms. C4H10, these two isomers are called isopropane or 2-methylpropane for the branched one, and simple butane for the first one. So butane has an isomer 2-methylpropane or isopropane. How many isomers could we predict for a molecule of pentane, C5H12? Well, if we take the 4-carbon chain, which is butane, and add a carbon to the end, we will get a 5-carbon straight chain called normal pentane. If we put it on the second carbon instead of the end carbon, then we have a branch called isopentane. If we put 2 carbons in the middle of 3 carbons, we have neopentane. And so in fact there are 3 isomers: pentane, isopentane, and neopentane. Those are your 3 isomers. Another type of isomer is called a stereoisomer. In this case, all the atoms are attached to the exact same atoms, but they're attached maybe in different ways. When you have a double bond cannot rotate like a single bond can. So here we have 2-butene, where the double bond is on the second carbon of a 4-carbon chain. When you have that double bond, you end up with 2 possibilities of where to put the 2 CH3 groups on the end. If you put them in a side-by-side fashion, like at the top, you have cis 2-butanes. The CH3s are close, like sisters. On the bottom, we see transbutene, where we've put the CH3s across the double bond away from each other, like a transatlantic flight, away and across the double bond. These are not identical. They would have different melting points and boiling points and properties. But you have exactly the same carbons and attached to the same carbons, just maybe attached in a slightly different way. Cis and trans isomers are called stereoisomers. So when you have compounds that have the same connectivity, same atoms connected to the same atoms, but they have different ways in which they are attached, then it's called a stereoisomer. Cis and trans isomers, because the alkene double bond is rigid and it's going to hold those groups in fixed positions, you're going to get cis and trans isomers possible. In the cis, the similar groups are on the same side, like sisters, and in the trans, they are on opposite sides, like transatlantic. Another kind of stereoisomers is something called chirality. Looking at these 2 molecules, you have a carbon bonded to hydrogen, chlorine, iodine, and bromine in both cases. So we have the same connectivity, but if you tried to put these 2 molecules on top of each other, you would find they're not superimposable. One is actually a mirror image of the other. So compounds that have the same connectivity, same molecular formula, but differ in the spatial arrangement of the atoms, these stereoisomers here. I think what you'd tell is that the left molecule is a mirror image of the right, but they're not identical. Mirror images are not identical. This is called chirality. Why can't I put my left glove on my right hand? Well, the left glove is a mirror image of the right glove, and so the left glove does not fit on the right hand. It's a mirror image of what would fit on your right hand. Your right hand is a mirror image of your left hand. Your right hand cannot replace your left hand, but in all respects it looks like your left hand, except that it's a mirror image. So chiral or mirror images are examples where you have two of something that do not superimpose, but in all other ways are alike. Your hands, your feet, left-handed, right-handed scissors. So let's take a look at these examples that are here on the screen and think about whether or not they are chiral or not. Chiral would mean they are mirror images and do not superimpose. Achiral would mean maybe they are mirror images, but they do superimpose. So will the right foot superimpose on the left foot? No, you can't make your right foot look like your left foot. It's a mirror image of it. How about a red circle? It's chiral. A red circle, the mirror image is another red circle, but the red circle on the right could sit right on top of the red circle on the left and superimpose. So it's achiral. Scissors actually have right and left-handedness, so they are chiral. Hands, of course, have right and left-handedness, so they're chiral. Now, if I had a shake in a glass here, I would say the shake in the glass is. Let me jump ahead to the snowflakes over there. The snowflakes, of course, are achiral because the mirror image is superimposable. But my shake is achiral until I consider the straw and maybe the things on the table, the little snacks on the table next to the drink there. If I include those as part of the picture, then we actually have chirality. Left and right-handedness, mirror images of each other. Now, what determines chirality in molecules? In molecules of organic compounds, it's having 4 different branches off of a carbon. Here we have 4 different atoms on the same carbon: bromine, chlorine, iodine, and hydrogen. The mirror image is not superimposable, as we see in letter B. Trying to put the mirror image on top means the orange bromine is on top of the chlorine instead of on top of the other bromine. If we line up the hydrogens and iodines, we cannot line up the bromines and chlorines. They're not superimposable. So, the same number of atoms are arranged differently in space, but they're chiral when there are 4 different groups attached to it. So keep that in mind. 4 different groups attached to a carbon is chiral. Your mirror images. So, checking our understanding of chirality. Identify each as chiral or achiral. Letter A here, we have carbon attached to hydrogen, chlorine, CH3, and a CH2CH3 group. Those are in fact 4 different groups, so we say that letter A is chiral. Many students think that this is achiral because the carbon is attached to carbon twice, CH3 and CH2CH3, but CH3 is not the same as CH2CH3, so this is in fact chiral. Letter B is achiral. It does have 4 things attached to carbon, but 2 of them are identical, hydrogen and hydrogen, and so that would not have the mirror image be non-superimposable. It would be superimposable. So letter B is achiral. C is chiral because the carbon is attached to 4 different things: hydrogen, chlorine, CH3, and Br. Okay, so to wrap up, this is the end of the organic module notes. There is a flashcard opportunity on this one. Chance to get 5 points by learning the first 10 alkanes, making flashcards of the first 10 alkanes. Study your functional groups. These are very important. You study your functional groups. The Mastering Chemistry will show us that there are multiple chapters here that we are looking at in our I believe in our version 10 of Timberlake textbook that we use, the paper copy that we have, the hard copy we have that handed out at the beginning of the year. It's, I believe, chapters 10 through 13. So there are multiple chapters. It's a fairly big amount of material to this module. But hopefully putting these notes online is going to help you manage the time for that. Thank you very much, and see you in class.